Okay, so let me just start with announcements. While I'm waiting for John. So you guys all turned in your problem set, thank you. That was the last problem set. And of course the finals next week, so let's talk about it.
I think you're off the screen.
Oh, am I?
Yeah.
Thanks. Okay, thank you. So, this is November 24th, Tuesday, November 24th. Okay. Oh, there's John, perfect. So last time when we did the midterm, I wanted to give you 2 hours. And I want to give you 2 hours for the final. And so since we're doing it during a class period, that means we either have to start early or we have to end late. All right, so last time we started at 8:45 and we ended at 10:45, and then I gave you like 10 more minutes to upload. So I think we did like 8:45 to 10:55 or something like that. Is that, does that work with people?
Pablo and I will be in a time zone an hour behind by then, so
Oh.
we probably prefer to end late, just so that we don't have to
Start at 9:30 and end late?
Yeah.
That's fine. I don't care at all.
Because then for us, it'll be start at 8:30.
Yeah, you need a strong cup of coffee.
Monster.
That's fine with me. Does anyone else have a preference?
Earlier as well.
What's that?
I'm cool with starting later rather
Or
than
we're
earlier.
starting on time. Like
On
Yeah,
time.
starting on
class
time, right.
and then-
Okay, that's fine with me.
Sure.
As long as no one has conflicts, which they shouldn't, I guess.
Yeah.
Okay. Okay, let's do that then. So we'll start at normal time. Start at 9:30. And then we'll finish at 11:30, and then I'll give you 10 minutes to upload. A generous 10 minutes, right? If like your phone crashes or something, and you have to run out, find a different phone. And so let's just say end at 11:30, and then exams emailed by 11:40, right? So it takes you less than 10 minutes to email exam, then you have a little extra time. Okay, is that okay with everyone? Check your calendar, shoot me an email if we need to adjust that, but that would be the plan. Okay, great. And so we should talk about what's on the exam. It's going to be the very, very similar format to your midterm. Okay, so probably 5 questions like the midterm. Do you guys think you had enough time to do the midterm? That's a rhetorical question, right? It's one of these things where I think you definitely should have enough time to do it. If you're running short on time, it's maybe because you, open book, open note exam is tricky because you can fall into the habit where you're spending all your time going through the book or going through your notes rather than actually thinking about things. So I would suggest that, the notes in the book are meant to be referenced, but if you're spending half the time going through the notes in the book, then you're not using that time for the exam, right? So I think you'll have enough time if you're not spending a ton of time going through the book and the notes. It will be cumulative because the class is cumulative. If you think about how the class is structured, the first part was mostly on formalism, the second part was mostly on applications, right? So it will be cumulative. Not much thermo. Equal or less thermo as the midterm, which was what, half a problem? Okay, so don't give yourself a headache studying thermo too much. Does anyone ever get a headache studying thermo? Okay. Someone had a question, is it more going to be focused on the homework questions or in class? Both, I guess. Right? I mean, everything's important. I don't want to say something's not important. The homework's important. what we did in class is important. The reading was important. You know, the homework and the class material kind of diverged a little bit towards the end. Right, in class we spent a lot of time talking about phonons. Maybe you had one question on phonons. And then, you know, you had questions on the homework, Maxwell-Boltzmann distribution, the classical partition function, which we didn't do in class. If I asked you, let's put it this way, I will try not to ask a question that deviates too much from discussions in class. Okay, so if I ask you a question that you say, oh, we didn't talk about it in class, it should be related enough to what we talked about in class that you should be able to solve it. How about that? So I'm not going to ask you a crazy question about the classical partition function that we didn't go over in class. Is that fair? You know, I like to ask about model problems. If you think about your midterm, how many of them were model problems? Almost all of them, right? And so because you know, real problems we need computers to solve, or the analytic result takes a while. So, you know, think about the types of things we've done and think about other model problems I could ask you similar to the midterm. Is what it's likely going to be. So that's my spiel. Questions, comments, thoughts? How should you study? Lock yourself in a dark closet. Try to remember as much as possible, and that sounds good. No, but I mean, really focus on concepts. You know, an open book, open note exam is nice in the sense that, well, it's good and it's bad, right? It's good because you never have to memorize anything, which is, you know, you guys shouldn't be tested on memorization, I think. It's bad because I'm not going to give you a question that's like directly like what we did in class, because I don't want you to just copy paste. You know what I mean? So if it was an open book, open note, maybe your questions would be, you know, more directly related, although I still hate to do that. But those are the pros and cons. It may look a little different than what we've done in class, but you should be able to extrapolate, similar to the midterm. So it's going to be the same idea as the midterm. Monte Carlo will not be emphasized, so this last week, today and Thursday, we'll be doing Monte Carlo. This will mainly be for the project. Okay, so I'm not going to test you on Monte Carlo methods on the final. There might be a question about the Ising model. If there is a question about the Ising model, it will be a simpler system that you can do by hand, which is probably a non-interacting system. Right? So, you know, these are, it's always good to think of what kind of questions I could ask you. I might ask you a question about the Ising model, but it's not going to be like what we're doing for the project, because you're not going to have a computer. Actually, you will have a computer, but I'm not going to make you use a computer. Okay, if you have questions or comments that come up, thoughts, send me an email. Do you guys want me to keep office hours next Monday? Do you want me to move it? Should we just keep it? We'll keep it next Monday? Okay. Oh, that's one more thing I wanted to discuss. I want to have, so we'll have office hours next Monday, and my phone's there. I was looking for my phone to look at my calendar. Okay. And then I want to have one office hours after your final, after Thanksgiving, where you can ask questions about the Monte Carlo project. So does anyone have I don't care when we do that. We could either do Monday, like normal, or we could do one of our normal class times. So that's Monday the 30th. Monday the 30th would be the first Monday after Thanksgiving. Maybe we should do it later.
We're saying the project is due the 10th.
The project is due the 10th. You know, I have mixed feelings. I want to do it earlier so people don't get stuck, but then if you do it earlier, then people haven't had a chance to look at it. Thursday the 3rd is a when do you guys have your quantum final?
7th.
The 7th.
Maybe not that, I don't know.
okay, the third is a nice median point. If
Third, yeah.
if we had to do
That's
it
fine.
before or after the third,
I think I would be cool with the third.
why don't
Yeah.
let's do the third,
Yeah.
and if we need to schedule on there, we can. Okay, so that's a Thursday.
Yep.
How are my Thursdays? I could probably. Should we just do normal class time, or is that too early? Normal class time. Okay. So, let's make that announcement 3. So, announcement 2 is Monte Carlo project. Due Thursday, December 10th, which is as far as I could push it before grades are due. And announcement 3 is we're gonna have office hours, 2 more office hours. Next week is the 23rd, okay, so Monday, November 23rd. And then what we just decided on is we're gonna do Thursday, December 3rd. Okay, so I don't have my calendar, so December 3rd, Thursday, right? And this is class time, right? Okay, great. Does that sound good to everyone? Okay, so that's a good plan. So 2 things left for the semester, the final and the project. And today we're really gonna go over the project. So let's get started. And again, we can talk about the final more on Thursday, or shoot me an email with questions. So I really want to go over the project, because the more we go over, the easier your life will be. Okay, I think I'm good over here. John, can you check me? Is this good?
Yes, you're on
Okay.
edge.
So we are finishing up Monte Carlo, and then we're gonna have to see how it works in practice. So Monte Carlo continued for the 3rd time. Okay. So let's outline the workflow of what we do in Monte Carlo. Okay, so let's write an outline. That's going to help us pick up where we left off. So the first thing you do in a Monte Carlo simulation is you choose an initial state of your system. Okay, that's number 1. Choose initial. I should say choose/prepare, because if you're doing it on a computer, you need to prepare your initial state. We'll talk about that. Okay, that's the first thing you do. And then what you want to do is you want to generate a trajectory of a bunch of different states. And there's different steps to generate a trajectory. And so the first step to generate a trajectory is try to make a Monte Carlo move. So attempt a Monte Carlo move. And the key point here is attempt. You're not necessarily going to do it. You're going to attempt a Monte Carlo move. Okay. In our case, this is choosing a spin at random and flipping it. Okay. Choose spin at random and flip. That's what your move's going to be. Okay. And we say there's some matrix alpha. Okay. And this matrix alpha tells us the probability of attempting a Monte Carlo move that takes us between 2 different states of the system. Okay, so alpha has to do with attempting the move. Then you're going to decide whether or not to accept the move, and that's where we left off. I told you that we're going to have to know the energy difference between your initial and your final state. So let me write that down. That's important. Mid-step, calculate, you always need the energy difference. Energy difference between, you can either call it your initial state, final state, the old state, the new state, right? Let's just say initial and final state. And you're going to use that energy difference for step 4, which is now you're going to decide whether or not you're going to accept the move. So step 4 is accept or reject the move. And just like we had a matrix alpha to tell us the probability of attempting to move, we have another matrix which tells us the probability of accepting and rejecting a move. We would give it this a nice name, ACC underscore underscore, the accept matrix. Okay, so that matrix tells us about step 4, and then 5 is repeat steps 2 to 3 a bunch of different times. Okay, 5 is repeat steps 2 to 4. How many times do we repeat it? Well, we've defined a length of the Monte Carlo trajectory as capital T, right? So capital T is the length of the Monte Carlo trajectory, so we need to repeat it this many times. Okay, so that's your outline. And so that's important to keep in mind, both for these lectures and also for the code that we're going to go over. Okay, so where were we last time? Last time we ended...
The acceptance probability matrix.
Yeah, so last time we were on step 4. We ended on step 4. Okay, so here's where we were. We learned how to compute the energy difference, and then we're figuring out how to accept and reject the move, and this led us to our discussion of detailed balance. Okay, so we were discussing detailed balance, which is what we need for step 4. And I made an analogy to microscopic reversibility, kinetics, if you remember. I do want to change my notation at this point. Last time we were using nu and nu prime. I think it's easier now to explicitly use I and F to specify whether we're switching between the initial and the final state. So let me just write it inside. I want to switch notation. Okay, switching notation is just going to be easier at this point. We were using state nu for an arbitrary initial state. We're going to use I for initial state. Okay, and we were using nu prime, and now we're going to use F for final state. Okay, and so I'm going to write my detailed balance equation down. Is just going to look the same as last time, except I'm going to replace the nu's with I. So we have the probability of being in the initial state, P sub I, times the IF element of the alpha matrix, times the IF element of the accept matrix, equals the probability of being in the final state, times the Fi element of the alpha matrix, times the Fi element of the accept matrix. Okay. So this is the same equation we ended with last time, but now I'm switching notation. Okay. And the way to interpret this is, remember the analogy we made that this is the same as saying the forward rate in a chemical reaction equals the reverse rate of a reaction at equilibrium. And so this is sort of a flow of probability from I to F. Flow of probability density from I to F. Okay, and this is the flow backwards, flow in reverse direction. Okay, and so what you're saying, just like in kinetics, is if you're at equilibrium, then the probability is stationary. The amount that flows forward is the same as the amount that shows that flows backwards. And so let me just write this down. This ensures detailed balance. It ensures that if we're at equilibrium, okay, well, let me just write it like this. Ensures no net flow of probability density for a system at equilibrium. If you're not at equilibrium, then there is a flow, but if you're at equilibrium, there's no net flow. For a system at equilibrium. Okay. So what are these probabilities? These are the equilibrium probabilities of the system. And so they're dictated by the ensemble. And so here, PI and PF are the equilibrium probabilities. Okay, as dictated by the ensemble. Okay, well, for the system in state I and F, okay, as dictated by the ensemble. Okay, and so we know where they are in the canonical ensemble. We're in the canonical ensemble. So in the canonical ensemble, we know where these are. Pi is e to the minus beta ei, the energy, over Q. Okay, and Pf is e to the minus beta E F over Q. Okay. So this equation encompasses the whole principle of how Monte Carlo works. Okay, so suppose you are. Do you even remember the critical temperature of the Ising model? It's like something like beta J is something like 0.4407. Okay, it's around 0.5. I remember 0.45, but I think it's actually 0.4407. You can check in your notes. Okay, so suppose you're at suppose you're at higher temperature. Okay, if you're at higher temperature than the critical point, your system should just be random spins at equilibrium, okay? Or at least it should have zero magnetization. Suppose you run a Monte Carlo simulation and you start with all your spins up, okay? You start with all your spins up. You know at equilibrium they should be randomized so that the net magnetization is zero. You're not at equilibrium. You're not at equilibrium. Think about what happens with the left-hand side and the right-hand side of this equation, okay? This part isn't changing. This is like your rate constant. Your rate constant isn't changing, okay? Suppose the left side is a state where all the spins are up. Suppose the right side is a state that's where it's randomized, okay? You are in a non-equilibrium distribution, right? And so you have more probability of your state being all spins up than given by equilibrium. So this means you're going to have net flow to the right. Okay, because you're starting with too much of this, your rate constant is just fixed, and so you're going to flow to the right. Whereas you have too little of this, your rate constant is fixed, So your reverse rate is lower and your forward rate is higher. And so that means when you run your simulation, you're basically gonna transition from all spins up to all spins random because of this equation, okay? If you're at equilibrium, then now the probability of your system being all spins up and the probability of your system being all spins random is the canonical distribution. And now the rates are equal, right? So the rates are only equal when your probabilities are the ensemble probabilities. And if they're not, then you have net flow towards equilibrium, okay? So by choosing these matrices in this form, it gives you net flow to equilibrium if you're not at equilibrium, and it gives you no net flow if you are at equilibrium. And so what your computer simulation is doing is converging to equilibrium, and then once you're at equilibrium, it stays in equilibrium. Does that kind of make sense? It's all based on this equation. This is the heart of Monte Carlo. If this equation wasn't true, there is no guarantee that you would actually get to equilibrium, and there's no guarantee that you would actually stay at equilibrium. In fact, you wouldn't stay at equilibrium. Okay? Actually, that's a subtle point. There's never a guarantee you're going to get to equilibrium. We can't really say that, right? I can't say how long it's going to take to get to equilibrium, but I can say there's going to be a tendency to get to equilibrium. And so you're going to explore that. That's going to be, you're going to explore that in question 1 of your project. Okay. So that's detailed balance. So now let's plug these probabilities into detailed balance. So let's label this 1. Okay. Let's label these 2. So combine 1 and 2. So we're just going to substitute these in for my probabilities. And the Q's are going to cancel out, right? Because I'm going to get a Q on the left, a Q on the right, so I'm going to drop that. We get e to the minus beta e I alpha if except if. That's the left-hand side here. I've thrown out the Q because it's going to cancel with the Q on the right. We get e to the minus beta e f alpha fi except fi. Okay. Now if you remember, the whole point is I'm still on step 4, right? I still need to figure out this matrix except. But now we're learning something about the matrix. It has to satisfy this equation. Okay? What can we say about alpha if and alpha fi? Anyone remember what alpha looks like? It's a sparse matrix, right? It's 0 if the states are not connected by, if they differ by more than one spin flip, and it has a constant value if the states are connected by one spin flip, and that constant was 1 over the number of spins, 1 over n squared if n by n is our lattice, right? So these elements are 1 over n squared. For states that are connected by one spin flip, and so alpha if equals alpha fi, right? So for our case, alpha if equals alpha fi equals 1 over n squared. If the system is connected by one spin flip. In this case, we know it is because it's a trial move, and the only moves we're doing are flipping one spin at a time. Okay, everyone kind of remember that? So what this means is my alphas cancel out, okay? And so my alphas cancel, alphas cancel, okay, and if we go up here, we get e to the minus beta e I except if equals e to the minus beta e f except Fi. Okay, and so now what I'm going to do is I'm going to bring this exponential to this side, I'm going to bring this to this side, and I get the ratio accept IF over accept Fi equals, let me write it like, well, e to the minus beta EF over e to the minus beta EI. If I divide two exponentials, I can subtract their arguments. I can write this as e to the minus beta delta E. Okay, and so this is a really important relation that you're going to use for step 4, right, where delta E is EF minus EI. Okay? So now you see why we need to do step 3. In step 3, we need to calculate the energy difference between the initial and final state. Why? Because it comes in right here. Okay? And so this is how you determine this matrix. Okay? This equation comes from detailed balance, right? It comes from detailed balance, and it gives you the necessary result, the necessary ratio between these two matrix elements to get a detailed balance condition that you use in step 4. So we have an underspecified matrix, right? Because all we're specifying is a ratio. We're not specifying each individual value. So we have a degree of freedom. And so normally what you do is you choose one and you fix the other to meet this criteria. And so let me just write this down. So the ratio, this ratio is fixed by detailed balance. Okay. And so we have freedom to choose one of these, and the other we have to choose based on this equation. So here's how we usually do it. So normal implementation is this, or the normal choice. Okay, here's our normal choice, and let me write it down and then we'll talk about it. Accept IF, it equals one of two things. We're gonna let it equal 1 if your energy difference is negative. We're gonna set it equal to 1 if delta E is less than or equal to 0. Okay? We're just making that choice. I'm free to make that choice. I only need to make sure the ratio obeys this relation. So if I make this choice, then my other condition is if this is not true, if delta E is greater than 0, since I've already made the choice for 1 here, it has to be equal to this. It has to be equal to E to the minus beta delta E. Okay? And note that this ensures that this ratio is true, because if delta E is less than or equal to 0 for going from I to F, it means delta E will be greater than 0 from going from F to I. Right? So if this is true, then suppose delta E is less than or equal to 0, then this equals 1. And this equals this. Except now, the delta E is always, well, let's just write it out. It's too confusing without writing it out. Let's look at 2 examples. Okay. So this is the choice we make. Let's check that choice. Check that this choice satisfies detailed balance. Okay, so case one, let's suppose that EF is greater than EI. Okay? EF is greater than EI. So, ACC IF equals what? If this is true, this thing's positive, it equals this, right? Equals e to the minus beta EF minus EI. Okay? And what about ACCFI? What does that equal? So ACCFI is if I'm going from F to I. If I'm going from F to I, my energy goes down. And if my energy goes down, I accept that move. Right? So this is equal to 1. Right? And so the ratio then, ACCIF over ACCFI equals this ratio. E to the minus beta EF over e to the minus beta EI. Check. Okay? So that case is fine. Right? Let's check case 2. The only other option is if EI is greater than EF. Okay. So if EI is greater than EF, I'm going down in energy when I go from I to F. So ACCIF is going to be 1. Okay. ACCFI, I'm going up in energy if I go from F to I. So that's this energy difference. But you have to be really careful with putting your indices in the right place. This equals e to the minus beta. Okay. I have an I here and I here, an F here and F here. Right? That means EI minus EF. Right? And you have to keep the indices the same. The order matters. Right? So if I have IF, I need IF. Okay? And so then if I take the ratio, ACCIF over ACCFI, then this thing flips and I get the same thing. Check. Okay? A little tricky. A little tricky. Did everyone see that? So basically, for the only two situations we can have, either the final state is higher energy than the initial state, or vice versa. If I always use this rule, for both directions, I always get my detailed balance condition. Okay? And so this is the rule that we use in our Monte Carlo to accept or reject a move. And we just verified that it gives us detailed balance, which verifies that if we're at equilibrium, we stay at equilibrium. And that's what we need for our simulation to be physical. So at the end of the day, this is what you're going to use. This is your criteria in your MC simulation. Right? So everything else was explaining why it works and why you're making this choice, but when you're writing your computer code, this is all you need. Okay, questions on that? I think we'll see. It'll become more clear when we actually look at the computer code. Okay, so now we're done. We've basically outlined 1, 2, 3, 4, and then we just have to repeat, and then we're done. Okay, so let me write a final diagram for what our simulation is going to give us. Let me keep my outline up. Okay. So basically the point is that you follow these steps to run a simulation, and then what do you get at the end? So the result of a Monte Carlo simulation is nothing more than generating a trajectory of different states of the system. Okay, what is the result? You have generated, at the end of the day, you've generated a trajectory of length t of different states of system. Okay? And so you're just going to have a bunch of different frames, right? Your result is going to be you're going to have different frames. And maybe we could draw those frames as boxes. So this would be frame 1. Sorry, let's use little t. We used little t before. Okay? Let's do t equals 1. Okay? This is just the label of the frame and the trajectory. So we have, actually, yeah, t equals 2, okay, t equals 3, all the way to t equals t, okay? And so all these boxes are different frames in your trajectory. Why do we call it frames? It's like taking a picture, right? It's like a picture frame. Because you're taking a picture of your simulation, and you're saying, here's what the simulation looks like at t equals 1. Here's what it looks like at t equals 2. Okay? For each of these, your system can be in a different state. So, what does new equal? I don't know. We don't know what it is. It's your initial state. Let's just call it A. We have some state of the system. Okay? So this is the state. All that matters is whether it's the same or different. So we start in initial state A. Then we do step 2, 3, and 4. Okay? Only two things can happen. Either I've made a move and I've accepted it, in which case I'm in a different state A, or I've made a move and rejected it, in which case I'm still in state A. So suppose I've rejected a move, then t equals 2 is also in state A. So here's MC, here I've rejected move. Reject, move. I don't know, I tried to move it in a different state and it just didn't work. Right? We use this criteria and I just didn't accept it. So I rejected the move and I'm still in state A. Okay, then when you go from frame 2 to 3, you've done another Monte Carlo move, and here you've accepted the move. Okay, and so here you're in a new state, B. Okay, so some of these are going to be in the same state if you rejected the move. But then at the end of the day, all your information is in all these frames. The T frames give you the information that you need to calculate things that I ask on the problem set, or to explore interesting physics, right? Because then what you do, then compute an average. Ensemble average. Okay? For example, I'm going to ask you to compute the average magnetization. Okay? Average M equals average magnetization. And we have a really simple formula to use for our average in a Monte Carlo simulation, but it depends on this trajectory. Remember, we have average M, we put a little capital T. I used G in the notes before, but now we're specifying we want the magnetization. This just means it's an average based on this trajectory T, and all we have to do is 1 over T sum over little t equals 1 to capital T M T, right? That's how you compute an average. And so what you need is you need all your frames, and you need to compute the magnetization in each of these frames, and you need to plug that in the formula, and you get an ensemble average. Does that make sense? So the point is, here's the procedure for how you do Monte Carlo. Here's the results of these different frames of trajectories, and here's what you do with it. Okay? Questions, comments?
Do we need to worry about the correlation between each frame?
That's a great question. You need to worry about the correlation between each frame. So, you will explore this in problem 1 a little bit. That question has to do with knowing whether or not you're at equilibrium. Okay, at the end of the day, you get an average, and that average is only going to be physically meaningful if your Monte Carlo simulation has reached equilibrium, and if all these snapshots are equilibrium snapshots of your system. Otherwise, it may not be physical because it's not equilibrium. And so Kevin's question relates to essentially understanding if you're actually at equilibrium. Okay, so we're not going to really talk about doing that. You could compute something like a correlation function to see how fast you're approaching equilibrium. We're going to look at it a different way. We're going to ask the same question, but you're going to do it sort of just brute force. So what I'm going to have you do is I'm going to have you run like 10,000 steps, and I'm going to have you run 100,000 steps and compare. And then I'm going to have you double the system size and do the same thing. So you will explore figuring out whether or not you've reached equilibrium, but using sort of a different approach then. Computing the correlation between frames would be a more elegant way to do it. But the brute force is simpler. So we're going to do it simpler.
So eventually, after some number of steps, our system's no longer going to change. We're going to reach equilibrium, and then we're just going to keep on getting the same average value over and over again.
Yep. Although your average depends, you need your entire trajectory to compute the average.
Yes.
So what you're going to do is
going for like an insane number of steps. The first number of steps that you did it, when it wasn't in equilibrium, wouldn't be contributing anything.
So let's talk about that when I pull the code up. So I'm almost ready to pull the code up. Maybe I should pull the code up now. Actually, it could be a good time. Is any question on this? Does this make sense? This is the procedure. Let's pull the code up. Let's do that, and we'll talk through. Okay. So what we're gonna do, I'm gonna send you guys a template code, and I always debate each year whether to have you write a code from scratch or send a template code. And number one, it's a little unfair if people have different levels of programming if I don't send a template code. And number two, it helps you avoid some of the time-consuming aspects. So I'm going to send you a template code. Let me see if I can